more expensive than the bomb. The economics of the B-29 Superfortress. 1. The most ambitious gamble expanded. The year is 1939. Europe descends into chaos as Nazi Germany's armies sweep across Poland, and the world watches with mounting dread as one nation after another falls before the German war machine. In the Pacific, tensions between the United States and Japan simmer beneath the surface, growing more volatile with each passing month. Japan's invasion of China in 1937 has established a pattern of aggression that shows no signs of stopping. American policymakers understand that war may be coming, perhaps sooner than anyone wishes to admit. Yet for the United States in 1939, war is still something that happens to other nations. American troops are not yet engaged in combat. American factories are not yet converted to wartime production. The economy, while recovering from the ravages of the Great Depression, still bears the scars of that catastrophic collapse just a decade earlier. In this atmosphere of uncertainty and foreboding, the United States military faces a strategic problem that demands immediate attention. If war comes to the Pacific, how will American forces strike at an enemy situated thousands of miles away, across one of the world's most formidable barriers of open ocean? The answer cannot be found in battleships or cruisers. Japanese naval power in the Pacific has grown formidable, and the traditional naval doctrine that emphasized the battleship as the ultimate arbiter of naval warfare is beginning to show its age. The naval war in Europe has already demonstrated that aircraft are becoming central to modern naval conflict. The answer, military planners conclude, must come from the air, but not from ordinary aircraft. The distances involved in the Pacific are so vast that ordinary bombers simply cannot reach their targets and return home. Something revolutionary is required. This is where the question of money enters the conversation. How much would it cost to build an aircraft that could do what no aircraft had ever done before? How much would it cost to create a machine that could fly higher, faster, and farther than any existing bomber? How much would it cost to push the boundaries of aeronautical engineering to such an extreme that entirely new manufacturing techniques would need to be invented? These were not abstract questions for military planners. They were questions with staggering implications for the American economy and for the future of the nation's industrial capacity. In the late 1930s, when this conversation first began in earnest, the concept of a long-range, high-altitude strategic bomber was still largely theoretical. Aircraft designers and engineers understood the principles involved, but the practical challenges of actually building such a machine were immense. The engines of the era, while impressive for their time, would need to operate under conditions that pushed the limits of what metal and mechanical engineering could accomplish. The fuselage would need to be substantially larger than any bomber yet constructed, raising questions about structural integrity and aerodynamic behavior. The speed and altitude requirements seemed to contradict each other. How could you build something that large and make it fly that fast and that high? In 1938, the United States Army Air Corps issued a preliminary specification for what it called a hemisphere defense weapon. The concept was deliberately vague, designed to stimulate creativity among aircraft manufacturers, while providing enough guidance to focus their efforts. The specification suggested an aircraft that could carry a bomb load of 2,000 pounds and fly at an altitude of 20,000 feet while maintaining speeds of over 250 miles per hour. For comparison, existing bombers of the era, aircraft like the Douglas B-18 or Martin B-10, typically flew at altitudes below 15,000 feet and carried similar bomb loads. The new specifications, while not demanding the moon, represented a significant step forward. But the preliminary specification would evolve. By 1939, military planners had become more ambitious. They began thinking in terms of an aircraft that could fly at altitudes of 25,000 feet, 30,000 feet, or even higher. They began to envision bomb loads of 4,000 pounds, 8,000 pounds, or more. They imagined range specifications that would allow the aircraft to fly missions that would have seemed impossible just a few years earlier. As these specifications evolved, so did the estimated costs. The design competition that would eventually lead to the B-29 was officially launched in 1940. Boeing, Douglas Aircraft, Lockheed, and Consolidated Aircraft all submitted designs for what the military was now officially designating as the XB-29. Each company understood that winning this competition would mean not just a lucrative contract for the initial production run, but the potential for orders that could sustain their company through years of war production. The stakes were unprecedented. Boeing's design, developed under the leadership of chief designer George Scherer and project manager Ben Robbins, represented an audacious commitment to technological advancement. The company's engineers proposed an aircraft that would be substantially larger than any existing bomber. They designed a fuselage that would be over 99 feet long, with a wingspan of nearly 142 feet. The aircraft would weigh nearly 135,000 pounds when fully loaded with fuel and bombs, far heavier than any bomber in existence. To achieve the required speed and altitude performance, the design called for 4 of the most powerful aircraft engines available: the Wright R-3350 double cyclone, which produced over 2,000 horsepower per engine. The projected cost of developing and producing such an aircraft was staggering. Boeing estimated that it would cost $330,000 to develop 2 prototypes of the XB-29. For context, this was during an era when the average American home sold for less than $4,000 and the average worker earned less than $2,000 per year. The cost of developing 2 aircraft was equivalent to the cost of purchasing 80 new homes or paying the annual salary of 165 workers for an entire year. This was money on a scale that most people in America could scarcely imagine. But the military understood that if the B-29 worked, if it truly could deliver on its extraordinary promises, the subsequent production orders would dwarf this initial development investment. Military planners estimated that if the program succeeded, they would want to order hundreds of the aircraft, perhaps eventually thousands. The economic implications were staggering. Boeing, like all the other major aircraft manufacturers in America, was still recovering from the economic devastation of the Great Depression. The aircraft industry had been particularly hard hit during the 1930s, as military budgets remained constrained and commercial aviation was still in its infancy. The company's workforce had shrunk dramatically from earlier years. The prospect of a massive production program for the B-29 represented not just profit, but a path to long-term stability and growth. When Boeing was selected as the prime contractor for the B-29 program in December 1941, a decision made just days before the attack on Pearl Harbor, though the timing was not directly connected. The company understood exactly what was being asked of it. This was not merely about building an airplane. This was about mobilizing an entire industrial ecosystem. The manufacturing processes that would be required to build the B-29 did not yet exist. The precision standards that would be demanded had never before been attempted in mass production. The coordination required between Boeing and dozens of subcontractors would be unprecedented. The company immediately began establishing new production facilities. Boeing's main plant in Seattle would be expanded dramatically. A new facility was constructed at Renton, just south of Seattle, specifically designed for B-29 production. Martin Aircraft established a major production facility in Omaha, Nebraska. North American Aviation created a B-29 production line in Kansas City. Bell Aircraft set up manufacturing operations in Marietta, Georgia. These were not simple additions to existing factories. These were entirely new facilities, built from the ground up, equipped with machinery designed specifically for the demands of B-29 production. The supply chain that would support B-29 production extended across the entire American industrial landscape. Aluminum producers ramped up output to supply the vast quantities of airframe material that would be required. Engine manufacturers, in this case Wright Aeronautical and Curtiss-Wright, were tasked with producing thousands of the powerful R-3350 engines that would power the fleet. Suppliers of instruments, electrical components, hydraulic systems, landing gear assemblies, and countless other components found themselves integrated into a supply chain of extraordinary complexity. The coordination required was staggering. A single missing component could halt production across multiple assembly lines. A delay in engine delivery could cascade through the entire program, preventing the completion of dozens of aircraft. A shortage of aluminum could force difficult decisions about which production lines would receive priority. The military created offices and bureaucracies specifically designed to manage these complexities, monitor production progress, and identify and resolve bottlenecks before they could cause catastrophic delays. Yet in 1941 and 1942, as these preparations were being made, and as the first prototypes were being constructed, the B-29 remained largely a theoretical proposition. Would it actually work? Would the four massive engines produce the required power without catastrophic overheating or other failures? Could pilots actually fly such a massive machine? Could the complex systems, the pressurized cabin, the remote-controlled gun turrets, the sophisticated navigation and bombing equipment all function reliably in combat conditions? The uncertainty was profound. The first flight of the XB-29 prototype occurred on September 21, 1942. It was a moment of tremendous significance, but also one tempered by the recognition that a successful first flight did not guarantee eventual success. The prototype experienced serious problems. The engines overheated repeatedly. The landing gear collapsed on one test flight. The pressurization system leaked. The remote gun control systems malfunctioned. Each problem required investigation and correction, consuming time and resources. Yet despite these challenges, the military commitment to the B-29 program never wavered. The decision to move forward with production had already been made, even before the prototypes had proven the concept. This was not a decision made lightly. It represented a gamble of enormous proportions, a bet that the problems would be solved, that the aircraft would eventually perform as promised, and that the investment would prove worthwhile. By the time Japan attacked Pearl Harbor on December 7, 1941, the initial contract for the B-29 program was already in place. The attack transformed the program's urgency overnight. What had been an ambitious peacetime investment in future capability became a desperate wartime necessity. The strategic vision behind the B-29, the ability to strike targets deep within enemy territory from bases far removed from the conflict, suddenly became absolutely critical to American strategy in the Pacific. This transformation would set the stage for one of the greatest and most expensive military programs in human history. The initial modest contracts that seemed expensive during the debates of 1940 and 1941 would balloon into figures that would dwarf the costs of almost any other military program. The B-29 would become not just an aircraft, but a symbol of American industrial capacity, American technological ambition, and American willingness to commit whatever resources were necessary to achieve victory. But all of that lay in the future. In 1941, as the nation mobilized for total war, the true scale of the commitment it was making to the B-29 program was not fully understood. Chapter Part 2. The Price of Warfare. December 7, 1941 changed everything. The attack on Pearl Harbor was more than a military catastrophe that left the American Pacific Fleet crippled in Hawaiian waters. It was an economic earthquake that reverberated through every corner of American industry. In a single morning, the B-29 program transformed from a speculative investment in future military capability into an urgent, desperate national necessity. The debate about whether the B-29 was worth its extraordinary cost suddenly evaporated. There was no longer a question of whether America could afford to build the aircraft. The only question that mattered was whether America could afford not to. In the weeks following Pearl Harbor, the U.S. military's strategic thinking underwent a fundamental transformation. The war in Europe, which had seemed distant and somewhat abstract to many Americans just days before, now felt immediate and threatening. The war in the Pacific, which had never seemed abstract at all, suddenly demanded solutions of unprecedented scale and ambition. Military planners understood that the Pacific War would be fought across distances so vast that traditional naval and ground-based tactics would be insufficient. Air power would be central to the conflict, and not just any air power, but the kind of long-range, strategic bombing capability that the B-29 promised to deliver. The immediate response from the military was to dramatically accelerate the B-29 program. What had been scheduled to progress at a measured pace was now pushed forward with desperate urgency. Production contracts that had been planned to develop gradually over years were now compressed into months. The initial orders for the B-29 began to expand from the hundreds into projections of thousands. Military planners were looking forward to a long war, and they wanted the B-29 to be the dominant weapon in their aerial arsenal. The financial implications of this acceleration were profound. Each completed B-29 cost approximately $639,000 in 1940s currency. To translate this into contemporary understanding, this was equivalent to nearly $1 million in today's money per aircraft. The price was not arbitrary. It reflected the genuine costs involved in producing one of the most sophisticated and complex machines ever built. Raw materials for the airframe, the engines, the instruments, and the systems. All of these represented substantial expenses. But the real cost driver was labor. The sheer number of hours required to construct, assemble, test, and prepare a single B-29 for operation was staggering. During the early production runs, each B-29 required approximately 45,000 hours of skilled labor to complete. This was equivalent to roughly 20 workers laboring full-time for an entire year to build a single aircraft. As production continued and manufacturing processes became more refined through learning and experience, this figure gradually decreased. Eventually, as the assembly lines achieved greater efficiency through repetition and optimization, the labor requirement dropped to approximately 10,000 to 12,000 hours per aircraft. But even this reduced figure was extraordinary by the standards of the era. When you multiply the per aircraft cost by the number of B-29s that would eventually be built, the total investment becomes almost incomprehensible in scale. Over 3,500 B-29s were produced during the war years. Simple multiplication yields a figure of roughly $2.2 billion in direct production costs alone. But this number represents only a portion of the total economic burden of the B-29 program. When you include research and development costs, the construction and expansion of manufacturing facilities, the training programs for workers and aircrew, and the operational costs of actually flying the aircraft in combat, the total figure climbed to nearly $4.5 billion by some estimates. To place this in context, the entire Manhattan Project, the vast, secret undertaking to develop nuclear weapons, cost approximately $2 billion. The B-29 program, by these estimates, ultimately cost nearly twice as much as the atomic bomb. An individual B-29 aircraft was more expensive than the atomic bomb that it would eventually be called upon to deliver. This was not the result of inefficiency or waste. This was the result of attempting to build something that had never been built before, at a scale that had never been attempted, while maintaining quality standards that were extraordinarily demanding. The economic burden extended far beyond the simple matter of purchasing price. Establishing production facilities required constructing new factories from the ground up, not as modifications of existing structures, but as entirely new industrial complexes. Boeing's Renton facility was built specifically to accommodate B-29 production. Martin Aircraft's Omaha plant was constructed on a scale that had never before been attempted for aircraft manufacturing. North American Aviation's Kansas City facility was designed and built with the assumption that it would operate at full capacity for years. Bell Aircraft's Marietta operation became a sprawling industrial complex that transformed the local landscape. These facilities required not just construction of buildings, but installation of specialized equipment. Machine tools designed to work with aluminum to tolerances of a few thousandths of an inch had to be purchased or custom-built. Assembly jigs and fixtures, structures designed to hold components in precise alignment while they were being riveted together, had to be designed and constructed for each major section of the aircraft. Riveting guns, welding equipment, hydraulic presses, and dozens of other specialized machines had to be installed and maintained. The capital investment in these production facilities was enormous, running into hundreds of millions of dollars when all facilities are totaled. The supply chain required to provision the B-29 program was a logistical marvel and a constant economic challenge. Aluminum had to be secured in quantities that had never before been demanded. The Aluminum Company of America, the dominant producer of aircraft-grade aluminum, was called upon to increase production dramatically. But aluminum production required electrical power on a scale that stressed regional power grids. Some aluminum production capacity had to be built specifically to support the B-29 program, requiring additional capital investment and creating vulnerabilities in the supply chain that military planners worked constantly to address. The engines presented another towering challenge. The Wright R-3350 double cyclone was one of the most powerful aircraft engines of the era, but it was also temperamental and unreliable in its early production versions. Each B-29 required 4 of these engines, meaning that 14,000 engines would need to be produced if 3,500 B-29s were to be built. Engine production became one of the greatest bottlenecks in the entire B-29 program. Wright Aeronautical and Curtiss-Wright were pushed to expand production continuously. Yet even with constant expansion, engine availability frequently constrained how many aircraft could be completed. The quality control demands of the B-29 program added substantial costs to manufacturing. Every component had to be inspected multiple times. Rivets had to be examined to ensure they were driven to precise specifications. Welds had to be tested not just visually, but through X-ray examination and stress testing. The aluminum sheets that made up the fuselage and wings had to meet specifications so demanding that aluminum producers had to develop new casting and rolling techniques. This quality control was not bureaucratic obsession. It was the direct result of the understanding that an aircraft that failed in flight would not only represent a loss of military capability, but the death of a trained crew and the waste of nearly $1 million of invested resources. Worker recruitment and training consumed enormous resources and represented a substantial portion of program costs. The B-29 required a workforce with skills that simply did not exist before the war. Boeing, Martin, North American, and Bell could not simply hire experienced aircraft workers because the experience required was too specialized and too new. They had to hire workers, many of them women entering the industrial workforce for the first time, and train them to work with tolerances and precision standards that were unprecedented in most industries. The training programs were extensive and expensive. New employees went through weeks or months of instruction before they were ready to contribute to actual production. Supervisory staff had to be trained not just in how the work should be done, but in how to teach the work to others. Quality inspectors had to be trained to evaluate work against specifications that were often new to manufacturing. The Boeing and other contractors had to establish schools, hire instructors, and devote enormous resources to turning inexperienced workers into skilled craftspeople capable of producing aircraft components with the precision required. The operational costs of the B-29 program were equally staggering. Flying a B-29 required enormous quantities of aviation fuel. Each combat mission consumed thousands of gallons of high-octane gasoline. A single B-29 operating from bases in India and staging through China could burn through fuel supplies that would have supported dozens of other military aircraft. The logistics of transporting fuel across the Himalayas to supply the B-29 campaign against Japan represented one of the greatest logistical challenges of the entire war. Fuel that could have supplied hundreds of fighters or medium bombers went instead to support the B-29 fleet. The training program for B-29 crews was exceptionally rigorous and expensive. Pilots had to learn to fly an aircraft that was substantially larger and more complex than anything they had previously encountered. Bombardiers had to master sophisticated bombing systems and learn to operate them under combat conditions, while the aircraft was subject to enemy fire. Engineers had to understand the four complex engines and be able to manage their operation across a wide range of flight conditions. Radio operators, gunners, and other crew members all required specialized training that could take months or even years to complete properly. Many trainee pilots died in accidents during preparation for B-29 operations. These were tragic losses of human life, but they also represented losses of invested resources. Each pilot who died in a training accident represented the destruction of months of training effort and the expenditure of training resources that could have been applied elsewhere. The training accidents were particularly concentrated in the early days of B-29 operations, when the aircraft was still new and its peculiarities not fully understood. Over 150 B-29s were lost to operational accidents or unknown causes during the war. Aircraft that simply disappeared during training flights or combat missions, taking their crews with them. The losses in actual combat added another brutal dimension to the economic accounting. The B-29 was not invulnerable. Japanese interceptor aircraft, though increasingly unable to reach the altitude at which B-29s flew by the later stages of the war, still managed to shoot down aircraft. Anti-aircraft fire took its toll. Mechanical failures, engine fires were always a threat, destroyed aircraft and crews. When a fully loaded B-29 was lost, the military lost an aircraft worth nearly $1 million, a crew of over a dozen highly trained men, and the bomb load that the aircraft was carrying. In total, approximately 12% of all B-29s built were lost to all causes: combat, accidents, and operational losses. Yet despite the extraordinary costs, despite the losses both in aircraft and in lives, the commitment to the B-29 program never wavered. Military planners understood that the Pacific War would be a long conflict that would require new capabilities and new weapons. The B-29 represented those capabilities in a form that no other aircraft could match. It was expensive, yes. It was causing economic strain throughout the American industrial system, yes. But it was also the future of American strategic air power, and in a war for national survival, cost could not be the determining factor in strategy. Part 3. The Technological Compromise. The extraordinary cost of the B-29 program was not an accident, nor was it the result of mismanagement or waste. It was the direct and inevitable consequence of pursuing specifications that pushed the boundaries of what was technologically possible in the 1940s. Every dollar spent on the B-29 program could be traced back to a specific technological challenge, a particular engineering problem that demanded a solution that no one had ever attempted before. To understand why the B-29 was so expensive, one must first understand what made it so difficult to build. The fundamental challenge that drove costs throughout the entire program was the matter of size combined with performance demands. The B-29 had to be large, so large that it could carry bomb loads that previous bombers could only dream about. The aircraft would need to lift 20,000 pounds or more of bombs from an airfield, fly thousands of miles through enemy airspace, deliver that payload to a target, and then fly back home. This was not a modest requirement. This was asking for something that violated the basic logic of aircraft design, which suggested that larger aircraft were slower aircraft, and that the ability to carry more payload meant sacrificing either range or speed. The design solution to this contradiction was sheer audacity. Boeing's engineers would build the largest aircraft yet attempted, but they would power it with 4 of the most powerful engines available. They would strip the airframe of unnecessary weight through the careful selection of materials and the optimization of every structural component. But even with these measures, the aircraft would still need technological innovations that pushed the current state of the art. And each of those innovations added cost. The pressurized cabin was one of the first major innovations that drove costs skyward. The military requirement for the B-29 to fly at altitudes above 30,000 feet was not arbitrary. At such altitudes, the air is so thin that unpressurized cabins become lethal within seconds. Pilots and crew members would lose consciousness from oxygen deprivation. Yet at 30,000 feet and above, Japanese fighter aircraft could not reach the B-29. The altitude advantage would be the aircraft's primary defense against enemy interceptors. But achieving this altitude while keeping the crew alive required pressurization technology that had been experimental and rare before the war. Pressurization systems were expensive to develop and even more expensive to manufacture reliably. The system had to maintain breathable air pressure inside the fuselage, while the outside pressure dropped to levels that would be instantly fatal. This required powerful compressors, complex valve systems, and intricate ducting that had to run throughout the aircraft. The system had to be redundant. If one compressor failed, backup systems had to take over immediately. The design and manufacturing of these systems demanded expertise that did not yet fully exist, requiring extensive research and development before production could even begin. The pressurization system on the B-29 was not simply installed and forgotten. It required constant maintenance and troubleshooting. Early B-29s experienced catastrophic pressurization failures in flight. Cabins would suddenly depressurize, rendering the crew unconscious. Pilots and crew members died in these accidents. Engineers at Boeing and at depots working on B-29 maintenance struggled to identify and fix the problems. Modifications were designed and incorporated into aircraft already in production. Retrofit programs required taking completed aircraft back to manufacturing facilities, disassembling sections of the fuselage, installing new components, and reassembling the aircraft. This constant modification and refinement consumed years and millions of dollars. The engines presented another towering engineering challenge that drove costs to extraordinary levels. The Wright R-3350 double cyclone was among the most powerful aircraft engines in existence, producing over 2,000 horsepower per engine. 4 of these engines, working in concert, would provide the 8,000 horsepower necessary to lift the B-29 and its payload to the required altitudes and speeds. But the R-3350 was also a temperamental beast that pushed the limits of what reciprocating engine technology could achieve. The engines were prone to overheating. The cooling system struggled to manage the tremendous heat generated by the massive pistons and cylinders. Pilots learned to dread the engine temperature warnings that would suddenly appear during flight. An engine that overheated could catch fire. Engine fires on a B-29 were often fatal. The aircraft would become difficult or impossible to control, and crews would have to attempt emergency landings or parachute into hostile territory. Throughout the war, engine fires caused the loss of dozens of B-29s. The solution to engine overheating required constant engineering work and modification. Cooling systems were redesigned. Engine cowlings were modified to improve airflow. Operating procedures were refined to help pilots manage engine temperatures more effectively. An entire organization of engineers focused exclusively on engine reliability and performance. Yet despite all of this effort and expense, engine problems remained a constant challenge throughout the war. The engines also presented supply chain complications. Each B-29 required 4 R-3350 engines. The production capacity for these engines could never quite keep up with B-29 assembly. Engine availability became one of the primary bottlenecks in the B-29 program. Completed B-29 fuselages would wait for engines. Assembly lines would slow down, waiting for deliveries of engines. The military and the contractors invested enormous resources in expanding engine production capacity, but the basic challenge remained: producing thousands of extremely complex, precision-engineered engines on a schedule that would satisfy the urgent demands of the war. The remote-controlled gun turrets represented another technological innovation born from the demand for capability, despite cost. Rather than stationing gunners at individual gun positions scattered around the fuselage, a design approach used in earlier bombers, the B-29 concentrated the gunners in a central compartment where they could use sophisticated optical systems and mechanical computing devices to aim weapons remotely. The gunner in the tail turret could see targets that he could not directly fire at because of obstructions. The fire control system would calculate trajectories, adjust for aircraft movement, and aim the guns with a precision that human eyes alone could never achieve. This system was revolutionary, but it was also extraordinarily expensive to develop and manufacture. The optical sights had to be precision instruments. The mechanical computers that calculated firing solutions had to operate reliably under the vibration and stress of combat flight. The hydraulic and electrical systems that transmitted commands from the gunner's station to the turrets had to be redundant and reliable. The sheer complexity of integrating these systems into a functioning whole required years of development and testing. The manufacturing of these systems required precision machining beyond what most American factories had previously attempted. Ball bearings manufactured to tolerances of a fraction of a millimeter were required for the smooth operation of the turrets. Electrical connections had to be made with reliability that would function at high altitudes and in the extreme cold of the upper atmosphere. Every component had to be tested individually and then tested again as part of the integrated system. The cost of these fire control systems, per aircraft, ran into tens of thousands of dollars, a staggering sum for a single system on a single aircraft. The electrical systems of the B-29 were monumentally complex. The aircraft required electrical generators capable of producing the enormous power demands of the pressurization system, the fire control systems, the navigation equipment, and dozens of other systems. Multiple generators had to operate in parallel, with automatic switching systems to maintain power, even if a single generator failed. The wiring harnesses running through the aircraft contained thousands of individual wires, each one connected to specific systems and components. The production of these harnesses required specialized equipment and highly skilled workers. The hydraulic systems demanded equally complex engineering solutions. The aircraft required hydraulic pressure to operate the landing gear, the flaps, the bomb bay doors, and numerous other systems. Multiple hydraulic systems operated independently so that the loss of one system would not render the aircraft unflyable. The pumps had to be capable of producing the required pressures. The hoses and fittings had to withstand vibration and stress. The hydraulic fluid itself had to remain effective at the extreme cold temperatures encountered at high altitudes. The fuel system had to transport thousands of gallons of aviation fuel throughout the aircraft while maintaining proper fuel distribution and preventing spillage. The B-29 carried so much fuel that proper fuel management was critical to aircraft control and performance. Fuel tanks had to be installed in the fuselage and wings in a configuration that balanced the weight properly throughout the aircraft. Fuel transfer systems had to move fuel between tanks to maintain proper weight distribution as the aircraft burned fuel during flight. The complexity of designing, manufacturing, and testing these systems added substantially to the overall cost of the aircraft. Every major system in the B-29 represented not just an engineering challenge, but an economic burden. The navigation equipment had to allow the aircraft to locate targets thousands of miles from home. The bombing systems had to deliver the payload with accuracy sufficient to justify the enormous cost of operating the aircraft. The communication systems had to allow crews to coordinate with each other and with ground stations across vast distances. Each of these systems was, by itself, a complex engineering feat that would have been remarkable if developed in isolation. On the B-29, they had to be integrated into a single machine. The construction process itself revealed the true cost of attempting to build such an advanced aircraft. The riveting process that assembled the aluminum sheets into a fuselage required incredible precision. Rivets had to be driven to a specific degree of tightness. Too loose and they would leak. Too tight and the aluminum would crack or the rivet would break. Workers learned to sense the proper tightness through the feel of the rivet gun, but quality control had to verify their work through inspection. Each B-29 required hundreds of thousands of rivets. The process of installing them was labor-intensive, and the verification process was equally demanding. Teams of riveting workers would move along the fuselage, installing and securing fasteners. Behind them came inspectors who examined every rivet, looking for any sign of improper installation. Some aircraft were reworked multiple times because inspectors found rivets that did not meet specifications. Welding, another critical manufacturing process, presented similar challenges. Welded joints had to be inspected visually and often tested through X-ray examination to ensure they had full strength. Any defective weld would be cut out, the joint reworked, and then tested again. This quality control was not perfectionism. It was the result of understanding that structural failure in flight could kill the crew and waste an aircraft that cost nearly $1 million. The cumulative effect of all these technological challenges was a manufacturing process of extraordinary complexity and expense. The aircraft that emerged from the assembly lines were marvels of engineering, representing the pinnacle of what American manufacturing could achieve in the 1940s. But each marvel came at a cost measured in millions of dollars and hundreds of thousands of hours of skilled labor. The B-29 was expensive not because it was overbuilt or because manufacturers were inefficient, but because it was attempting to do something that had never been done before, at a scale that had never been attempted, with precision standards that pushed the limits of what was possible. Part 4. The Legacy of Expense. August 15, 1945. Japan formally surrenders, ending the Pacific War and bringing World War II to a close. The news spreads across America with electrifying speed. In cities and towns across the nation, Americans pour into the streets to celebrate the victory. The war that had consumed the nation's attention and resources for nearly 4 years is finally over. Yet even as celebrations unfold, the machinery of American industrial mobilization begins to wind down. The economic consequences of demobilization would rival the upheaval that had accompanied the wartime mobilization. The B-29 program comes to an abrupt halt. Hundreds of aircraft sit in various stages of completion on assembly lines in Wichita, Omaha, Kansas City, and Marietta. Workers who had been building B-29s for 3 or 4 years suddenly find themselves without jobs. The contracts that had promised years of steady employment are canceled. Production orders that stretched into the future are terminated. Military requirements that had seemed urgent and absolute just days before are suddenly irrelevant. The world has changed overnight. The economic shock of this demobilization hits the aircraft industry with devastating force. Boeing's workforce, which had swollen to over 80,000 workers at the peak of wartime production, shrinks to a fraction of that size within weeks and months. Martin Aircraft, North American Aviation, Bell Aircraft, and dozens of other contractors face similar catastrophic reductions in employment and production. The specialized manufacturing facilities that had been constructed specifically for B-29 production suddenly become liabilities rather than assets. Some facilities are converted to peacetime production, others are sold to private companies, and still others are simply dismantled. The financial losses are staggering, contracts are terminated, and the military must compensate manufacturers for work already completed, but for aircraft that will never be delivered. The government absorbs losses on tooling and equipment that was specifically designed for B-29 production and has no other use. Production facilities constructed at enormous expense are abandoned or converted at substantial loss. The process of demobilization creates a financial hemorrhaging that extends far beyond the simple cessation of new orders. Yet even as the shock of demobilization reverberates through the aircraft industry, the strategic implications of the B-29 program become increasingly clear. The aircraft had proven itself in combat. The B-29s that flew from bases in India and China had demonstrated that American bombers could strike at the heart of Japanese industrial capacity. The raids on Japanese cities, including the final devastating firebombing campaign, had been conducted by B-29s. The 2 atomic bombs had been delivered by B-29s. The aircraft had been absolutely central to the defeat of Japan. Most importantly, the B-29 had fundamentally altered the economics of modern warfare. It had demonstrated that technological superiority could be purchased if a nation was willing to commit sufficient resources. It had shown that the industrial capacity of a nation could be mobilized to produce weapons of staggering sophistication. The B-29 had been more expensive than the atomic bomb, not because of waste or inefficiency, but because it was more essential to achieving victory. Without the B-29, the atomic bombs would have remained theoretical weapons, with no means of delivery. The implications of this lesson were profound and would shape military thinking for the next several decades. Before the B-29, military aircraft were still relatively inexpensive compared to major capital assets like battleships. The battleship had dominated naval strategy for centuries, and even as naval aviation began to supersede battleships as the dominant naval weapon, aircraft were still viewed as tools that supported the traditional fleet structure. The B-29 changed this calculation permanently. After the B-29, military strategists understood that a single strategic bomber could cost as much as an entire naval task force. A single aircraft, with a crew of fewer than a dozen men, could carry more destructive power than a battleship armed with the largest guns that could be mounted on a warship. The pilot of a B-29, flying thousands of miles into enemy territory, could exercise more strategic impact than an admiral commanding a fleet. The revolution in warfare was complete, and the B-29 had been the vehicle through which that revolution was demonstrated. The aircraft themselves did not disappear when the war ended. Hundreds of B-29s were retained by the U.S. military for operations in the post-war era. Some were converted to reconnaissance missions, equipped with cameras and other surveillance equipment instead of weapons. Others were converted for weather research, equipped with instruments to study atmospheric conditions and weather patterns. Still others served as airborne command posts, serving as flying headquarters for military operations. Several B-29s were captured by the Soviet Union when the war in Manchuria ended. The Soviets acquired both intact aircraft and access to American technical documentation. Soviet engineers immediately began the work of reverse engineering the B-29. The result was the Tupolev Tu-4, a Soviet bomber that was essentially a copy of the B-29 with minor modifications. The Tu-4 would serve as the foundation for Soviet long-range bomber development throughout the late 1940s and 1950s. American technology that had cost billions of dollars to develop was rapidly reproduced by Soviet engineers, extending American bomber technology into the Soviet arsenal and demonstrating the dangers of allowing advanced military technology to fall into enemy hands. The B-29 remained in the inventory of the United States Air Force well into the 1950s. As strategic thinking evolved and nuclear weapons became the dominant focus of military planning, the B-29 was viewed as an interim solution, a powerful aircraft that could deliver both conventional bombs and nuclear weapons, but ultimately destined to be superseded by newer designs. The B-47 Stratojet, with its revolutionary swept-wing design, eventually displaced the B-29 in the strategic bombing role. The B-47 would be followed by the B-52 Superfortress, which would dominate American strategic bombing for decades. Yet the B-29 remained operational longer than anyone in 1945 had expected. The last B-29 was retired from active U.S. Air Force service in 1954, 9 years after the end of the war that had spawned it. Some aircraft continued flying in other roles: weather reconnaissance, high-altitude research, and photo reconnaissance. Well into the 1960s, the longevity of the aircraft vindicated the investment in quality and durability that had driven costs so high during production. The financial and economic impacts of the B-29 program extended far beyond the military sphere. The program had fundamentally transformed American manufacturing. Workers who had learned to work with tolerances of thousandths of an inch did not forget those skills when the war ended. Supervisors and engineers who had learned to manage large-scale precision manufacturing operations carried that expertise into the post-war era. The manufacturing techniques developed for the B-29 program became the foundation for precision manufacturing in American industry for the next several decades. The suppliers and subcontractors who had supported the B-29 program adapted their facilities and expertise to other applications. Aluminum suppliers who had ramped up production to support the B-29 program found post-war markets for their increased capacity. Manufacturers of precision instruments, electrical components, and hydraulic systems had learned to operate at scales and standards that exceeded anything the civilian market had previously demanded. The defense industry that emerged in the post-war era was built substantially on the foundations established by the B-29 program. From a purely economic standpoint, the B-29 program represented both a tremendous success and a cautionary tale about the costs of military innovation during wartime. It succeeded because the aircraft did precisely what it was designed to do. It projected American military power across the vast distances of the Pacific. It destroyed Japanese industrial capacity, Japanese cities, and Japanese military forces with devastating effectiveness. It served as the delivery platform for weapons that would define the entire second half of the 20th century. Yet the program's success came at a cost that would have seemed impossible to justify under any other circumstances. Only the desperation of total war could have convinced American decision-makers to commit such extraordinary resources to a single weapon system. Only the existential threat posed by Nazi Germany and Imperial Japan could have justified the mobilization of American industrial capacity on such a staggering scale. Under any other circumstances, the resources devoted to the B-29 would have been distributed across multiple programs or used for other purposes. As the years passed and the Cold War evolved, the lesson the B-29 had taught would be repeated again and again. Technological superiority required investment. Maintaining military dominance meant accepting enormous budgetary burdens. The weapons of the modern age would be extraordinarily expensive. The B-52 Superfortress, which replaced the B-29, would cost even more per unit. The intercontinental ballistic missiles that followed would cost more still. The nuclear-powered submarines that would carry missiles would cost billions of dollars each. The trajectory established by the B-29 would extend into the modern era. Military spending on advanced weapon systems would become a permanent feature of American defense policy. The concept that a single advanced aircraft could cost as much as a major capital investment would become normal rather than shocking. The B-29 had established the precedent that technological superiority was worth any price, and that precedent would shape military spending for decades to come. The Cold War would be fought, at least partially, in the realm of expensive weapons systems. The Soviet Union, attempting to match American military capabilities, would pour resources into developing comparable bombers and missiles. The arms race that defined the Cold War was, in many ways, an extension of the logic that had driven the B-29 program during World War II. Both superpowers understood that technological superiority, while expensive, was essential to maintaining strategic advantage. Looking back from the perspective of the 21st century, the B-29 program appears as a crucial turning point in military history. It was the moment when the nature of military technology fundamentally changed. Before the B-29, military hardware was expensive, yes, but it was still viewed as equipment that could be replaced or upgraded within the realm of normal military budgeting. The B-29 changed that calculation. After the B-29, military technology became so expensive and so complex that entire national economies could be reshaped by the demands of acquiring and maintaining advanced weapons systems. The Manhattan Project, the effort to develop nuclear weapons, would ultimately cost less than the B-29 program. Yet the atomic bomb once delivered, required far less maintenance and support than a fleet of B-29s. The bomb was a one-time use weapon, while the B-29 represented a continuous demand on resources for maintenance, crew training, and operational support. In this sense, the B-29 was more expensive not just in initial acquisition cost, but in the ongoing long-term expense of maintaining strategic capability. In the end, the B-29 was more expensive than the bomb because it was more essential. It was the platform that made the bomb relevant. It was the aircraft that demonstrated American industrial and technological capability. It was the weapon system that proved that if a nation was willing to commit sufficient resources, it could accomplish what had previously seemed impossible. The costs were staggering, running to billions of dollars. The human toll was significant, with crews lost in accidents and combat. Yet the aircraft accomplished its mission, and in doing so, it fundamentally altered the nature of modern warfare. The legacy of the B-29 program extends beyond the aircraft itself. It established principles that would guide military spending for the rest of the century and beyond. It demonstrated that technological advantage was purchasable if a nation was willing to pay. It showed that an advanced weapon system could cost more than atomic weapons, and that the expense was justified by the capability it provided. The B-29 was, in the end, not just an aircraft. It was a statement about the nature of power in the modern age, that power could be purchased, that it had to be purchased, and that the cost, however extraordinary, would be paid if the strategic necessity was great enough. The aircraft that had seemed so expensive and so controversial during the debates of 1940 and 1941 had become, by 1945, indispensable to American victory. The decision to proceed with the program, despite its astronomical costs, had been vindicated by history. The B-29 had proven itself not just as a weapon of war, but as a demonstration of American capability and commitment. It had established a precedent that would guide military innovation and spending for generations to come. In the calculus of total war, the B-29 had been not an extravagance, but an absolute necessity, and the price paid for its development and production represented the truest measure of American determination to spare no expense in achieving victory.